Okay, we'll go ahead and get started with today's webinar. I want to thank everyone for joining us today. This is Melissa from the National Ocean Sciences Bowl National Office in Washington, D.C. Again, thanks for joining us. I'm just going to start with a real quick introduction of NOSB, because I think we have a few people who are joining us who may not participate in our competition. So the NOSB is an academic competition for high school students across the United States, and they get tested in their knowledge of all things related to the ocean and ocean sciences. And each year, at least for the past few years, we've had a theme for the competition year. This year happens to be the science of oil in the ocean. So our webinar series here is particularly for our coaches. It's something where they can get some background on new and upcoming research and science and be able to learn more about the ocean sciences if they're interested, but also incorporate what they learn into their teaching, either in their classroom or with their study sessions with their teams. But as you all know, we do open this up to any educator who's interested in learning about the topic. And just so you know, today's webinar, the webinar from last week, and our one that we will have next week, we do record them all. So if you know someone who is missing today's webinar, we will have the recordings up on our website. If you go to our homepage at www.nosb.org, right on our front page is a link to our professional development webinar series information, and you'll find anything you need about the series there. So for today, our agenda is that we'll have a 1-hour presentation, and then we'll have 30 minutes for you to do questions and answers. Just so you're reminded, you are all currently on mute. This just helps with the presenter so that there's no background noises. Everyone can hear him. This chat box at the very bottom of your screen, that's where you're going to want to type in all your questions that you have today. At the very end of the presentation, I will read the questions aloud to our presenter. So you feel free to type them in now or as they pop up during the webinar, or you can wait till the very end. Also, feel free to provide feedback either in that chat box or email at us at nosb@oceanleadership.org. We love to get feedback on how you use these webinars and how they help you and your students prepare for the competitions or just in general. That helps us retain funding to be able to offer this series. Also, our presenter today has said that he would be willing to answer any questions that you might have offline. So again, feel free to email us and we will get those to our presenter so he can answer them for you. So our guest expert for today is Dr. Arthur Mariano, and he's at the University of Miami Rosenstiel School of Marine and Atmospheric Science. And today he's going to be presenting on ocean currents and the 2010 Deepwater Horizon oil blowout. So our first webinar was sort of about the chemical composition of oil. Today is going to be more about the transport and tracking of oil. Just to give you a hint, you should be, if you have a few different tabs open on the WebEx screen, make sure that you clicked on the one that says Arthur Mariano's screen. That's the one that's currently going to be showing the presentation. One other tip, currently you probably see the video screen, the participant screen, and the chat screen. If you don't want to see those, there's little X's up in the right-hand corner. You can close them for now, and then you can also use the 2 arrows to make the actual presentation full screen. So just in case you need a little help with that. Again, feel free to type into the chat box if you're having any problems or any questions. Otherwise, we are going to get started with Arthur. Arthur, go ahead. You are now on.
Thank you, Melissa, for that introduction, and I'd like to thank everybody for joining us today, and a big thanks for all you do as teachers. I'm a member of the CARTH Consortium, and the work I'm going to be talking about has been funded by the Gulf of Mexico Research Initiative. Shown right now is a visible image of the oil spill during its first phase. We're going to go through the various stages of the oil spill and how the ocean currents affect the transport and dispersion of oil. Okay, first of all, whenever I give a public talk, I like to tell folks that science is just the best guess. Some guesses, of course, are better than others. And predicting where oil goes and its effects is harder than rocket science. And that's one of the messages I want to convey to you. This is not an easy science to do. Before we get into the oil, let me mention something about the surface of the ocean, what moves things around. As you all know, in March of 2011, there was a major tsunami off the coast of Japan. The first object that went across the Pacific Ocean was a soccer ball, and there's a very nice story about they found the soccer ball and they actually returned it to the owner. And the reason that soccer ball made it across the ocean before anything else is the fact that the winds are very strong and push that ball that's riding on the surface of the ocean. When you look at what moves stuff on the ocean surface, it's a combination of wind, waves, and ocean currents. And of course, more closer to the surface, the ocean currents become important. And when you have objects sticking out of the surface, for example, bobbing up and down like a lost boat, the winds become very critical in predicting where things move. Shown here are two scenes that are out in the Pacific Ocean right now. These are objects from the tsunami that have ended up in convergence zones. It's a fact that when you look at less dense objects that are less dense than seawater, for example, plastics, sargassum weed, drifters, they will end up in surface convergence zones. Due to the flow of the ocean, due to the ocean dynamics, there are places where ocean water comes together and converges. Now the ocean water, the seawater, can feel the three-dimensional effects and move downward in the water column in these convergence zones. These objects, including oil, are less dense, so they cannot feel the vertical movement, so they get very highly concentrated in this convergence zone, which has a very dire consequences about oil spills, is that in places the oil concentrations can be very great due to these convergence, and we'll see that. So here's the first visible image of the Deepwater Horizon oil blowout a few days after it happened. What you can see here is the Mississippi Delta, the northern Gulf of Mexico, and just southeast of the tip of the Mississippi Delta, we see an anomalous blob on the ocean surface, and that's the oil that's coming up there. And the first thing you notice that it's fairly concentrated and that there's some filaments, long, thin concentrations of oil coming out of the main blob. Here's an aerial photograph of what was happening at the edge of where the oil was protruding into the cleaner water. So this is an example of a front. This front is being caused by density differences between the oil-water mixture versus just pure water. The dynamics along the front are very complicated. One of the things you notice in this picture is there's a lot of small-scale wiggles in the distribution of the front. And we have found by looking very closely at the circulation and the dynamics of the Gulf of Mexico that these small-scale processes are very important for determining where oil goes in the ocean. Now as we get closer to the surface, here's an image from a boat showing how sharp that front can be. Anybody that spends any time fishing in the ocean or the Gulf of Mexico goes out looking for these fronts where different water masses come together, because it's a place where there are convergences, and we get bait fish converging in those fronts, and the large pelagics follow. Now, we get even a closer view of the oil. The one thing you should take home from this picture is that the oil distribution is patchy. That if you look closely in on the oil, there's places where the oil concentration is very great and it's very thick. And just 10, 15 centimeters away from this very large, strong concentration of oil, you have places where the water has very little oil on its surface. So oil concentrations vary by many orders of magnitudes due to ocean dynamics and the velocity distribution. Even getting further magnified, a very close look at the oil. This actually looks pretty, even though it's oil floating on the surface, and we can see the much different colors of the oil. And again, on very small scales of less than an inch, the concentrations of the oil can vary by 3 to 4 orders of magnitude. Now this becomes important when the oil starts reaching the land. So here in this picture, showing the oil reaching some of the marshes areas in the northern Gulf of Mexico, one thing you notice in this picture to the left of the landmass is that most of that area is, most of the water is oil-free. On the other hand, there are places where the oil is highly concentrated. And the fact that it's highly concentrated means it will have more toxic effect on marine life. Getting even a nice shot looking into the marshes, one of the things you notice in the center part of the picture is that even in the marshes, there's pools of places where the oil concentration is fairly low, and then there are other pools where the oil concentration is much greater. Now, besides hitting the marshes, we all know the oil came onto the beach. Shown here is a wave breaking onto the beach, bringing oil onto the beach. One of besides just oil coming on to the beach, one of the things we normally find on the beach after an oil spill is tar balls. Tar balls are left behind products. It's when all of the lighter gases have escaped the oil, heavier parts of the oil has sunk. It leaves these patties behind. For scales, you can see the size of these. They have a tendency to be a few inches in size, and depending on the spill, they could be many different colors. Now, during the oil spill, I actually found a couple dozen oil patties on the coast of Hollywood, Florida. I brought them to the U.S. Coast Guard, thinking maybe oil did get around into the Straits of Florida and reached Hollywood. But it turned out that my samples and about 200 other samples between Key West and Forest Pierce showed that those tar balls were from oil that was not the Deepwater Horizon blowout and probably came from ships that were taking advantage of being able to unload their bilges in the middle of the spills. Okay, so there's a lot of processes that influence the distribution of oil from a blowout. So at a depth of 1,500 meters, there was an engineering accident that allowed a very large mixture of oil and gases to escape the seafloor. The oil and gases are much less dense than seawater, so since they're less dense than seawater, that density difference will drive a buoyant flow from the deep ocean up to the surface. Now, this flow is being driven by density differences. Those density differences are large, so the flow velocities are large. This creates a velocity shear, places where the velocity are large, and then away from the central part of the blowout, the velocities are much weaker. This velocity shear helps enhance the turbulent mixing of the oil and gas mixture, and we're going to show you a numerical simulation of how that happens in a few moments. As this oil and water mixture comes out, some of the heavier part of the mixture sinks immediately to the ocean floor. So in the vicinity of the wellhead, of course, you have the greatest concentrations of the oil, and the concentrations of the oil will decrease as you go away from the blowout. Now, also, as part of the mixing process, as we'll see in the animation, the oil mixes with the seawater and forms subsurface plumes. These subsurface plumes are then spread by deep ocean currents, deep ocean eddy activities, mostly along the topography. So we expect to see a lot of the oil in the depth ranges of on the order of 1,500 meters where the spill came out. So then the oil reaches the surface. And on the surface, the ocean currents are stronger. The ocean eddies, which is a type of ocean variability that looks like small hurricanes in the ocean, but they're much, much slower. The thermodynamics are much different, but they consist of significant rotary motion. The mean ocean currents and these eddies help transport the oil away from its initial location. Winds also push the oil. Waves also push the oil. And as the oil is on the surface, the oil starts to weather. Sun, light, and especially in warmer temperatures and under good wind conditions, the oil will start evaporating. The benzenes, the lighter gaseous elements leave the oil, usually within the first 24 hours or so, leaving behind a product that's a little bit heavier. As the oil spreads out and mixes with the water, some of the heavier parts fall down. And so even away from the wellhead, you will have oil going into the water column from the surface. And as the oil gets closer to the coast, a completely different set of coastal dynamics take over. And we're going to describe a number of these processes in detail in the next half hour. And if you want to learn about each of the numerical modeling activities, the experiments, and about these processes in more detail, you can visit the CARP website. Now, here's a diagram schematic put out by Exxon in 1985. I'll be honest, it's not correct. There's some problems with it, but this shows the different processes affecting the oil distribution and the time scale. So on the bottom axis is the time scales where they believe these processes are important. The thickness, the amount of black associated with each of the processes is that it's either stronger or weaker. So in the first week or so, there's a lot of spreading and advection of the oil by ocean currents. And to be honest with you, the second thing that Exxon has, advection, is really wrong, because it really depends on the ocean velocity conditions and where the oil goes after it hits the surface. So that advection line should be much thicker in different places. In the first week, a lot of it evaporates, leaving tar balls on the surface. A lot of it gets dissolved into the water column. There's natural dispersion, and in this case, emulsifiers were added, dispersants to help the natural emulsification. Emulsification you can think of as if you take vinegar and oil in a salad dressing bottle, shake it up a little bit, you have the oil and vinegar mixing with each other. There's a photooxidation effect where light excites some of the atoms on the surface of the oil and produces a reaction releasing some of the lighter elements. And then eventually the oil reaches the sediments and has shoreline stranding and becomes a major mess to clean up. And a lot of you have heard about the oil-eating bacteria that's out there. It's interesting that Exxon has that effect pretty much becoming small after a year. Most scientists would have the biodegradation effect lasting on timescales of decades, not years, this schematic shows, which is put out by one of the oil companies. How much oil was spilt? Oh, about 200 million gallons was the estimate. Basically, 20 million gallons of the oil was skimmed and burned in real-time recovery operations. 34 million gallons was actually recovered by siphons, and I guess they were able to reuse that oil. 50 million gallons of oil is evaporated in this area. It's happened at a time of the year where the temperature is warm, and you do have significant winds that aid that evaporation. We believe on the order of 10 million gallons or so of the oil is on the bottom as tar mats. That oil will be there for a while, maybe decades. The oil-eating bacteria will have a all-you-can-eat buffet in the vicinity of the wellhead for a while. They estimated 40-something million gallons became tar balls, reached the beaches, or ended up in the sediments, and that 48 million gallons is totally dissolved in oil droplets in the water. Now, 48 million gallons sounds like a lot, and it is, but realize the volume of the Gulf of Mexico is on the order of 10 quadrillion gallons, and there's a flow in the loop current that between the Gulf of Mexico and the Florida Straits that's on the order of 7 to 8 billion gallons of water per second. Okay, here's a numerical simulation. We're going to show you what happens when oil and gas comes out of the bottom of the ocean. So first thing you notice, it shoots up fairly quickly because there's a very large density differences. There's a lot of turbulent mixing. The oil gets concentrated, and you can see a lot of it is reaching the surface in the simulation. But the most important thing besides the oil reaching the surface is that at depths we see subsurface plumes forming and spreading out. So the less dense oil mixes with the water till it reaches an equilibrium density, and then the effects of ocean currents and turbulent mixing help spread that oil out. Now, whenever you run a numerical model, you need to make sure it's accurate, and one way to do that is to look at real data. And shown here in the next slide is a subsurface oil plume that was found by a remotely operated vehicle by Keneally and his colleagues right after the spill. And you can see that at a depth of a few hundred meters above the spill, there's a very large concentration of oil. And you can also see there's a couple of other places where the concentration is a little greater at depth. And so we believe that the modeling we're doing of these plumes is in the right direction. Now, what happens when the oil comes to the sea surface? Now, shown here on the surface is a front. There's a front in this area due to a number of factors. One, due to the wind-driven ocean circulation. Other, due to the effects of the Mississippi River, and also due to the background mean circulation. Now, along this front we have a sea of ocean eddies. These ocean eddies are very vigorous. They have velocities on the order of 20 up to 50 centimeters a second, and occasionally more in the deeper Gulf of Mexico. And what we're going to see is what happens when the oil reaches the sea surface. And the main message here is that the sea of eddies are very efficient at spreading the oil out horizontally, and also because there are convergences associated with the flow with these eddies, the oil does get concentrated into filaments. So let's see that simulation now. So the oil is getting near the surface. We have a bunch of ocean eddies operating on the oil, and you can see on the right-hand side there's a filament coming out of that, and that's due to advection by the eddies. The eddy is wrapping the oil around with its strong rotary velocity. Now we have eddies on the left side of the oil surface, also advecting the oil further away from its surfacing location. So we can see that the eddies help spread out the oil, and they do this very efficiently, and they help to form filaments. Okay, one of the things when the oil spill was going on, there were forecasts of the oil location. So shown here in the light blue is the forecast for April 26th, and you can see from the color scales for the different dates, and then shown here is the last forecast. I think that's a light orange color on May 1st, and you can see that the models are predicting that the oil is going to grow in size, and that has to do a lot by turbulent advection, by the background mean flow, and by the ocean eddies. Also, one of the things that was noted here, of course, is that the control of the winds on the oil. So one of the reasons most of the oil at this particular time is going to the north of the initial spill location is because of the direction of the winds. Shown here are another set of forecasts. This is now from May 2nd to May 7th, and you can see that by May 7th, the area is even getting larger, and you can see that the oil is starting to impinge the Mississippi River Delta. Shown here is a visible image of the oil from the part of the spill, and one of the things you can see in this image are the filaments coming off the main oil patch as suggested by our numerical simulations. As a matter of fact, there was a very large filament visible, and shown here are two different images of that. The one on the left is from a synthetic aperture radar, which measures surface roughness. Oil reduces surface roughness, so in areas where there's reduced surface roughness, you could detect the oil. This is a nice instrument. Unfortunately, at very low wind speeds, it doesn't work too well because there's not much surface roughness, and so the surface roughness signal is very small. And at very large wind speeds, the oil and water starts mixing efficiently, and it's very hard to tell the two apart in the SARM image. Shown to the right of it is a well-known image you may have seen before that was shown a lot of times during the spill. This is a visible image from the MODIS, Aqua, and Terra satellites. A series of visible images were taken by those two satellites. Those satellites are NOAA satellites. They're used a lot. For example, they produced a nice cloud maps. They show us where the hurricanes are. We use data from these satellites to estimate sea surface temperature, ocean color, and other important ocean parameters. And during the early part of the spill, the visible images were, when you have a cloud-free day, was one of the best ways to detect where the oil was going. So in both of these images, independent data sets, we see a very strong filament being torn apart from the main oil blob, and that's due to a large eddy that's in this area, and it's affecting the filament around the edge of the eddy. Here's a close-up of the SAR image near the Mississippi Delta, showing the unhappy consequences of the oil getting into the marshes. Here's another SAR image. This is getting to a point where they're starting to actually reduce the flow of the oil due to the different cap-in operations, siphon operations, etc. Again, more oil at the end of July, getting into the Mississippi Delta. At the time, I was advising the White House about the oil spill. Obama's science advisors were calling me up. They were pretty diligent, you know, Sunday morning, 7 o'clock, some phone calls. And they asked me what I would do with the oil in the marshes. I recommended that they burn the oil in the marshes. It would have some short-term consequences, but the long-term effect would be there'd be a lot less oil there than there is now. And unfortunately, every time we have a major weather event like tropical storms and hurricanes, the oil that's in the delta is getting further pushed up into that ecosystem. There's a very large program now looking at ways to efficiently remove the oil from this area. I think burning it would be a good idea. It would have been a political PR nightmare to do that, but you have to keep realize there are a lot of mature ecosystems around the world, like the New Jersey pine barrens, that are controlled by fire. So the oil reached the beaches. Here's a typical cleanup scene. So a large amount of folks in hazmat uniforms are out there cleaning oil off the beach on very hot days, very dirty work. So a lot of the beaches now, when you look at the surface, you really don't see oil. However, if you go to many of the northern Gulf beaches and dig down, let's face it, sand's like kitty litter. The oil seeped down the sand, and in many places there is a significant concentration of oil at 1 to 2 foot depths in the sand. I'm going to mention here a few minutes, why did Florida get lucky? Why didn't we get covered in oil like the northern Gulf of Mexico? Basically for 2 reasons. One is that the oil weathers and evaporates, so a lot of the oil is removed from the system before it was able to get into the loop current and the Florida current. And also we had a very lucky dynamical event for us. A loop current formed an eddy, which I'm going to talk about now. So here's a picture of sea surface temperature that's measured by the MODIS, Aqua, and Terra satellites I mentioned before, and also with some input from the European satellites. The brighter colors are higher temperatures, and that circulation feature you see there is the loop current eddy. As time goes on, and right now we're looking at the beginning of July right now, one thing you can notice is that the Gulf of Mexico becomes very warm, and it's very hard to see the loop current. It's very hard to see the ocean eddies, and there's a lot of clouds in this area. So as you reach the summertime, the MODIS, Aqua, and Terra satellites weren't as useful for detecting the eddy and the ocean dynamics, which are needed to predict where the oil moves. So here's a blow-up of this particular area, color enhanced by Dr. Mitch Roffer from Roths, and you can see this is the eddy that's being formed. So normally the loop current connects the northern Gulf of Mexico to the Florida current through the Florida Straits, and there would be a direct flow, and you would see warm water that would be directly connected from the northern Gulf into the Florida Straits. But now you can see the eastern edge, the southern edge of the warm water is being formed into this eddy feature, and also notice on the western and northern part of this eddy feature, there's very small sub-mesoscale eddies that are helping to mix the ocean. And if you look near the Mississippi Delta in this picture, you could also see eddies very close to the Mississippi Delta and a signature of an ocean current with the warm water flowing along the coast. So these loop current eddies, on the average, form every 9 to 14 months. We were very lucky that it happened to form at the time of the spill. Lucky for us in Florida, helped keep the oil away. Shown here is a image from 1998 showing a loop current eddy, a very beautiful image of it, so that's why I included it. And the other important thing about these loop current eddies is they contain a significant amount of warm water with a strong rotary flow on the order of 1 to 2 miles an hour. When hurricanes pass over these loop current eddies and they take the heat out of the surface waters to help fuel the hurricane development, the eddies are able to evac more warm water because of their speeds into the area, providing more fuel for hurricane development. And for example, Hurricane Katrina, one of the reasons it was a very strong hurricane when it hit the northern Gulf of Mexico was that it went over a loop current eddy and was intensified by it. Okay, I'm going to start talking about predicting where the oil goes. And first off, I'm going to show you a very bad prediction. Some of you may have seen this. It made the national news, unfortunately. And it predicted that the oil from the Gulf of Mexico was going to get entrained into the loop current, entrained into the Florida current, and spread along the East Coast and spread into the entire Northwest Atlantic. First of all, this didn't happen is because they used average velocity conditions. The process of averaging velocity conditions produced a velocity field that really doesn't look like and is not exactly like the velocity field at any given time because of the peculiarities of trying to average data that changes a lot in space and time. So that was a problem with this. They didn't put weathering in, the fact that some of this oil was going to be evaporated away and wouldn't stay as oil through its entire journey through the Gulfstream system. The other problem with this picture, in terms of the fact that it made the national media, it's kind of a nice picture showing really bright colors, and everybody took this as very large oil concentrations, but these colors actually represent very low concentrations of oil. So now I'm going to talk about why it's hard to predict oil. So what do you need to predict oil? What do scientists need? We need to know the oil type and the amount, the location of the oil. We need to know about ocean currents. We need to know about wind speed and direction. We need to know about temperature because it affects evaporation, and there's other things we need to know. One thing we can note is that the winds and the waves have a tendency to push the oil at 3% of the wind speed, and so for a 20-knot wind, that's on you a little over a half a knot, which is on the same size, is the same speed as the ocean currents. So the winds and the waves are as important as the ocean currents, and also the winds are very important for determining the ocean currents in this area. And then, of course, we need theories of how nature works. We need to, put on a science hat and come up with our best guesses on how nature works. And based on these theories, we will build numerical models and try to do numerical simulations about how nature works. So what exactly do we do in these numerical simulations? First, there's a whole bunch of different physics. We have a buoyant and plume, we have air-sea interactions, we have ocean mixin, current advection. And all these different physical processes, we're able to write mathematical equations, usually based on conservation laws. Shown here is a set of equations known as the Navier-Stokes Equations. So these are mathematical equations. They're nonlinear, they're coupled, they're very difficult. No one's been able to solve them in their entirety, which is good. It gives us physical oceanographers a job security. And what we need to do with this, since we can't solve it analytically with a pencil and paper, is we need to write a computer code to solve these numerically. So we take the equations of motion, write a numerical version of them, a discrete version that we could run on a computer. So we need to know, to predict the future, you need to know the present. So at time equals 0, we need to know what the ocean currents are. We need to know what the initial location of the oil is. There's some examples shown on the left of the slide. And we need to know what the winds are, the waves are. We could put what I did in my codes is I brought in the measured winds and put the effects of the winds and waves together at a value of 3% of the wind speed. Then we need to run this on a supercomputer, a large computer that's fast with many processors, and do prediction. So this is analogous in the ocean what they do in the atmosphere for numerical weather prediction on a daily basis. And it's important to add that the prediction of the winds from the atmospheric models are very important for driving the ocean currents. Now, how long can we predict the movement of oil for? Well, it depends where you are, what time of the year, but on the average, we could predict things for 2 to 7 days. Why is that? Well, in a simple word, nonlinear fluid dynamics. This effect was known by Wielander in the 1950s. Shown in the upper left-hand panel is a picture in the most upper panel of an eddy interacting with a strong current. Shown are the pressure distributions. And in that flow, they put a checkerboard pattern of black and white particles, and they looked at what happens to the particles. And if you notice, the evolution is right below the picture. There's 5 snapshots increasing in time from left to right and then to the bottom row. And we can see by the 4th and 5th picture in particular, there are very long filamented parts of the dyed water particles being stretched out by the eddies like we've seen in the visible and SAR images of the oil. The other thing is if you concentrate on the black and white 2 squares in the upper right-hand corner and look at how they move apart in time, you can see that places that were fairly close together over time spreads very quickly. Shown in the upper right-hand panel is a prediction of what happens when you put particles in the Gulf Stream. Now, these particles were a few kilometers apart, and after 1 week of doing a numerical simulation, they're 300 kilometers apart. So very small differences in the initial location of the oil, small differences in the values of the currents and the winds produce very large differences in where the oil goes. This is due to nonlinear dynamics. There was a lot of theoretical work done in the ocean and the atmosphere, starting with Wielander and then Lorentz's famous work in the 1960s. Shown here is a butterfly attractor, and he showed in numerical simulations that small perturbations in atmospheric conditions cause large changes in atmospheric forecasts far away from the location of initial perturbation, and made a comment that a butterfly could flap its wings in one location and change the weather in another location. Shown here are 5 estimates of simulated oil locations. Now, in these simulations done by my colleagues at the Navy Research Lab, we're very happy that they're part of CARTH, they're one of the world's best group of modelers. What they did for these simulations is in each simulation, the oil is coming out exactly the same, in the exact same location. They perturbed the ocean currents and the wind forcing by the amount of uncertainty, the amount of error we know about these estimates of the ocean currents and winds. And you can see, I'm just showing you 5 of the ensembles that come out in these simulations. You can see the distribution of oil is much different in the different simulations, even though everything is the same in these simulations except for small differences in ocean currents and wind forcing. I'm going to show you a simulation now off the Florida coast. This is where I live. Now, we had a small box, 10 miles by 10 miles, 100 square miles. Time is running up. You can see the counter. We're on 1 day now. And you can see after 1 day that the oil that was, either could be an oil spill. The other thing this could be is uncertainty in initial position and how that uncertainty in initial position grows due to ocean dynamics for search and rescue applications. And let me just stress, this is a very simplified flow. This is not the realistic Florida current, but a simplified version of it just to show the effects of dispersion on oil. So we can see that after 3 days, that a patch that was normally 100 square miles has evolved into a patch that's now 10,000 square miles. So if you're looking for somebody that's lost at sea, it becomes very difficult to find them after 72 hours, and that's the normal cutoff for U.S. Coast Guard search and rescue. So let me just say that the transport and dispersion of oil is governed by nonlinear processes. Small changes in the ocean currents or wind used for prediction leads to significant changes in the forecast of oil trajectories. So we must have accurate ocean current and wind information. And the best way to get accurate information is to go out and measure things. Now, there's 2 different viewpoints for observing, analyzing, and modeling fluids. One is the Illyrian viewpoint that's fixed in space. So you put an instrument at a fixed location, like a current meter, and it measures velocity. Now, another approach is Lagrangian, which is following a tagged fluid parcel. So somehow we tag a fluid parcel either with dye or with some type of drifter, and we follow it in time. The Illyrian viewpoint is named after Euler, a Swiss mathematician, and Lagrangian is named after Lagrange, a very famous mathematician. Okay, so here's an example of an Illyrian method. Current meters fixed to the sea bottom. The current meters are shown with weather vane looking devices to help it line up with the flow. It helps give it direction. And then in these current meters, there's little cups that are very efficient at catching the water flow, and they spin around, and the amount of spins is related to the amount of flow. They're anchored by heavy anchors. Here at University of Miami, we used railroad wheels, and we have an acoustic release. So you set these out in the ocean. You come back a year later, 6 months later, 2 years later, you send down a 17 kilohertz signal. The acoustic release will hopefully release your instrument. On the top part of this instrument, you can see a circle, and that is to represent positive buoyancy spheres that are put on these current meters. One, to keep the current meter taut in the water column so it stays at the depth you want. But once you release the anchor weight, those glass spheres, which are in plastic hard hats, bring this instrument up to the surface. The other way is Lagrangian, following a tagged fluid parcel, shown as one of the first Lagrangian instruments from the RV Challenger that went around the world measuring biogeochemical physical properties of the ocean in the later part of the 19th century. And they were able to measure currents by visually tracking this, which actually leads to large error. Through the history of oceanography, we've used a lot of inexpensive drifters. Richardson and Stommel did a famous experiment looking at ocean dispersion with parsnip. We used IBM cards for all you old-timers out there. Remember programming in the old days? We weren't allowed to touch a computer. We had to give it instructions by IBM cards. And so there's a lot of IBM cards lying around labs, and they turned out to be pretty good followers of water. Of course, the old message in a bottle, people have marked coconuts, and in the upper top right panel showing a dye experiment with minograph paper going out, and they'll be taking aerial photographs of that dye and then going on later measuring concentrations of it to determine how the dye moves around. Now, we also have natural drifters in the Gulf of Mexico and off the east coast of the United States, most of the Northwest Atlantic, Caribbean, Gulf of Mexico, is sargassum weed. Sargassum weed is very important because it is the nursery for a lot of the large pelagic fish in the Northwest Atlantic. In the image on the lower right, you can see a lot of the bait fish that's attracted. Sargassum forms these masses we can see in the lower left-hand corner that line up with the convergence zone. So one of the big fears during the oil spill is we know that the oil will end up in these convergence zones. The sargassum is in these convergence zones, so we expect to see very large concentrations of oil in areas that are extremely important for the health of the fisheries. And the long-term consequences of that will take a few years to figure out. So let's mention some other ways people have measured circulation. One is the old message in the bottle. Here they put a lot of bottles out at Riley's Hump. It turns out to be a spawning site for mutton snapper. And they recovered the bottles in different locations up and down the Florida Key, Dade County, Broward County, and Palm Beach, showing that the mutton snapper spawn in this area and then help populate the Florida Reef system. Drift cards were used a lot. There was a major project in the Gulf of Mexico in the late 1950s where they put drift cards out, a lot of them along the West Florida shelf to measure the circulation. And we're still getting some drift cards back. A couple years ago, I received a drift card from Fort Pierce. We also had one drift card that was found off the north coast of Brazil, and none of us could figure out how it ever got there. There may be an oceanographic explanation, but we haven't been able to figure it out. We think somebody may have picked up a drift card and released it down there later on. Through time, there's been some interesting items that have been lost in the ocean that people like Kurt Ebsemeyer have used to track ocean currents. There was the great Nike sneaker accident in May of '90, where the sneakers then started turning up a year or two later along the west coast of the United States and Hawaii. And then the Rubber Ducky, very famous accident in January '92, fairly close to the other accident scene, real strong winds in that area. And one of the things they noticed is these duckies ended up in the Arctic Circle area, and they actually came around Greenland and came down the northeast and northwest part of the Atlantic. And 11 years later, they actually found ducks making landfall in Scotland and Maine. Now, with any data set, sometimes you get some anomalies, and they're really interesting, and they actually take a lot of our time to analyze. They found some ducks in '92, late '92, that there's no way those ducks could have gotten from the accident site to those locations in '92. So they were ducks probably lost by some other means. One of the workhorses of measuring near-surface ocean currents is the Davis code drifter. Code stands for California Ocean Dynamics Experiment, was the first use of these drifters. And shown here are these drifters. They have fabric used for vanes to help with their water following capability. In this case, this drifter is shown with an antenna. It was transmitting either to land-based stations or planes were flying over to receive the signal. Now we pretty much transmit to different satellites, either the Argo satellites on the NOAA system or one of the Iridium satellites or GPS-based satellites like the SPOT system. Also shown on these drifters are 4 pieces of styrofoam tied to rope to the drifters. What they do is help keep the drifters in the water during large wave events. And this particular drifter is what our Karth used in the Gulf of Mexico. Other drifters are shown here. The middle panel on the bottom is an example of one of the code type of drifters that has been instrumented with different instruments. And the whole set of 3 panels in the top are the workhorse of near-surface drifter measurements being put out by AOML and other countries from around the world. They consist of a Holy sock that has a size depending on either the mini or the maximum on the order of 5 to 20 meters. They're drogued for depths of usually on the order of 10 to 15 meters, though people have done experiments with these drifters drogued at deeper depths like 50 to 100 meters. And the ball that you see in the upper left-hand panel and in the surface in the middle one contains electronics where it transmits to the Argo satellite system. So the Argo satellite system, we're able to tell where that drifter is at a particular time. And by putting all the drifter positions with time, you use a little calculus, calculate some derivatives. The position is velocity. We get the velocities. These drifters also have other instruments. Most of them have sea surface temperature measurements on them, which is helped to use to calibrate the sea surface temperature measurements from satellites. Some of them have sensors on there to measure salinity, and some of them measure atmospheric pressure, and they also have a really interesting way to measure wind velocity with a vane-given direction, and actually a sound sensor measuring the ambient ocean noise, which is a strong function of wind speed. Now, shown in the bottom right-hand panel is a spider-looking type of drifter that's being developed, that has been developed in Europe, and that drifter is specially designed to try to track oil movement. So this drifter moves like oil, much more so than any of the other drifters shown in this picture. So let me show you one of the first set of data that came from the near-surface drifters. Here's a drifter that was put in 1977, year day 105, near a longitude of 70 west, a latitude of 36 north. And you can see that this drifter has significant rotary motion. This was ring bob, and this is one of these eddies. This is a large Gulfstream eddy known as a Gulfstream Ring. In this case, it was a cold core ring, and we could see it had very significant rotary motion. That's why we see all the looping. And the fact that there's a mean background flow, so this drifter is spinning around in the eddy, and as it's spinning, it's being pushed by the mean background flow, and that's why we get looping. And there are places where there's some cusp-like motion, and those are the places where the rotational speed of the eddy is equal to the translational speed of the background currents. So let me show you some more trajectory. This is one of my favorite ones, launched in Florida Bay on just inshore of the Keys. And we can see that this drifter trajectory, you can see the dates. So the places where the dates are fairly far apart, the velocity is great. Where the dots are close together, the velocity is weak. So we can see as this drifter moves up the Florida coast, it's in the Florida Straits. Offshore of the Carolinas, it's deflected a little bit offshore by a topographic feature known as the Charleston Bump. We get a little action in the slope water, it slows down, then it gets caught in the Gulf Stream and maps out Gulf Stream meanders, both the troughs and the crest, before getting then entrained into the slower subtropical gyre circulation that also has significant eddy variability. The speeds in the gyre are on the order of 10 to 20 centimeters a second, and the speeds of the Gulf Stream is over 200 centimeters a second. So there's an order of magnitude of difference in speeds from the interior of the ocean as compared to the strong western boundary currents. Here's another beautiful drifter launched off of Iceland. This makes 2 counterclockwise loops around the subpolar gyre. And it's amazing this drifter did this, and you can see how closely the paths follow year after year. Shown in the dotted line is a particular bottom contour, and one of the things you notice, even for a drifter who's floating at the surface on the order of 10 meters below the surface, there's strong topographic control in an ocean that's 4,000 to 5,000 meters deep in that location. Well, one of the things we do with the drifters, we take all the speeds, we put them together, and what this shows out in black are speeds greater than a meter a second, on the order of 2 miles an hour. And what we can see in this picture is the Yucatan current in the lowermost left feeding into the loop current, feeding into the Florida current. feeding into the Gulfstream system, and then once we start getting east of 50 degrees, the Gulfstream system starts bifurcating. We could take all the data, we could plot how much data we have to know where we could believe it and where we need to put more data. We could look at the energy level of the surface ocean, and we could look at the speed. And one of the things you learn from this is that we have the strongest and most energetic flows along the western boundary currents. That has to do with the fact that the Coriolis rotation changes with latitude. We also have very strong flow in the equatorial region, driven by the trade winds, and very strong flow in the Antarctic circumpolar current region due to the strong winds in that particular area. So we're going to play a video here. There may be a little lag between the audio and the picture, but bear with us. So this is the video.
Bob is doing well, very well indeed. That's because he's helping the planet with his specially designed body. Bob drifts with ocean currents and communicates his position and speed back to scientists on shore. Today, Bob is in the Gulf of Mexico. Sometimes, if the conditions are right, he can get stuck in what is known as the loop current. In the loop current, Bob meets larval lobsters from Mexico. The currents may take them through the Straits of Florida towards the reefs of Florida and the Caribbean, where they can grow into legal-sized delicacies. If there's a hurricane, Bob doesn't evacuate, he stays and measures valuable data about the violent surface currents. Thanks, Bob. Bob can help in all kinds of emergencies, including when a pollutant is released into the water. Bob drifts with the yucky stuff in the ocean current and sends his data to be fed into computer models that help scientists predict its fate. Not only that, but if somebody gets lost at sea, who can help figure out where the ocean currents may take him? Bob can. To track Bob and his friends and to learn more about what he does, visit carthe.org.
Okay, so as that cute little video introduced, the CARTH group designed and deployed over 300 drifters in about a week's time. The largest drifter experiment ever done at one time in the northern Gulf of Mexico. Some of the drifters were tracked for as long as 6 months, and we collected over almost 6 million data points. So here's one of our sampling patterns, an S-shaped pattern. The line moving quickly is the ship, and shown are clusters of drifters. So in this one S-shaped pattern, we put out 90 drifters and 30 clusters of 3 each. And you can see the initial movement of the drifters. Most of them are going to the south, and they're staying fairly close together. Shown here is a video of the other drifter trajectories. There's different drifters corresponding to different colors, showing you where the well site is. We concentrated the experiment around where the well site is. One of the things you see is significant rotary motion, some of it very small scale. That's due to a process called inertial oscillations. That's the free solution to the water movement. We also see larger oscillations associated with the eddies. So some of these, most of the drifters, you can see, left the area where we deploy them. Some of the drifters, like especially the ones going to the southeast right now, really quickly were caught in very strong circulation features. So from all these drifters, we're able to help improve the estimates of ocean velocity. We also looked at how water disperses and looked at dispersion statistics and published a number of papers of those, and more are coming out. I'm going to continue the animation of this. Now, one of the things we're going to see coming up, close right now, is a track of Hurricane Isaac that went through our drifter array in August of 2012. And one of the things you notice is the size of the circles increased because the water velocity increased greatly due to the hurricane. The inertial oscillations got larger. And the other thing you notice is now there's a bunch of yellow dots on the Mississippi Delta. The drifters were blown onto shore by the hurricane. And as I mentioned earlier, this is the problem with the fact that there's oil still in the marshes. When you're going to have these very strong atmospheric and oceanic events, because there is a strong storm surge associated with the hurricane that will take this oil and move it further back into the ecosystem. Here's another simulation of this hurricane. It's a very important event, so we did a lot of simulations of it. And also shown in this particular one is the sea surface height, and you can see that near the coast, the waves are over, the significant wave height is over 25 feet, which again will have a significant impact on any oil along the coastline. And also you see in the simulation all the drifters ending up back on the coast. Here's a very interesting animation showing why it's difficult to predict oil movement. So there's 3 drifters here, but you're only seeing 2, but now you're finally seeing the 3rd. So these 3 drifters were launched initially 100 meters apart. There's a time going, you see Tuesday the 31st, Wednesday, we're on day number 10. So on day number 10, one drifter is all by itself. The other 2 drifters actually came back together, and it looks like the one drifter by himself is going to win the race to get the furthest away from its launch location after the first, we're now up to 20 days. It got caught in a significant dynamical feature. You see how quickly it moved. But now it got kicked out of the dynamical feature and slowed up. And now, like the horse coming out of the backstretch, we have this other drifter totally past it, as it actually ended up staying in that strong dynamical feature. So after 30 days, 3 drifters that were just 100 meters apart have now moved to distances on the order of 200–300 kilometers apart. So this shows the difficulty in predicting the movement of oil. We also did experiments along the coast. Actually, what happened there? That went a little too quick. In December of 2013, tracked drifters near the beach. We tracked them with drones, helicopters, dives, using boats and jet skis. It was a pretty fun experiment. I wish I was up there, but I couldn't make it. Shown here are the crew putting out some of the drifters. These drifters were a different design. They were designed so they actually stay in the surf. As you can imagine, when waves break, they would throw the plastic drifters up in the air and onto the beach. These drifters had a tendency to stay more in the water. Shown in the bottom right is some of the dye release experiments. And one of the things you notice in the dye release experiment, the bright colors that are been funneled into a fairly narrow area and going offshore. This is a prime example of a rip current. And what this dye shows is what you've all hear about. If you get caught in a rip current, the rip current will have a tendency to be parallel to the beach. So you would swim with that rip current. And then if you look in the lower left-hand corner, you can start seeing some of that dye is coming back inshore. And part of this experiment was to learn more about rip currents, since they do cause a number of drowning fatalities every year. We've seen some of the classic ideas of what rip current systems look like, which are counter-rotating rotary flows right next to the coast. But we've also seen some of these rotary flows not being counter-rotating, but being next to each other with the same sense of rotation, which really hasn't been described too much in the literature. So here's an example of one launch of drifters off Desden. We could see that they initially start going offshore, and then they start approaching the beach at a later time. So I'm going to show you now an animation of all the drifter launch. There's one vector that you could see around 30.1 north, 87.6 west. That's the wind speed. And you will notice the direction of the wind speed forces the direction of the drifters, which way they go a lot. So right now the wind's blowing in. Most of the drifters launched are going in. Now finally we got the wind blowing offshore a little bit. Now there's one fast trajectory in here. There's a drifter on the boat, so we kept track of the boat. So there's one real fast moving back and forth, and that's the boat. So now you can see a significant offshore breeze, and the drifters do venture far out of off the coast. So we launched them near the beach. They're hitting depths of 50 meters. Now the wind changed direction. The drifters headed back toward shore. The wind changes direction again. The drifters head offshore. So this is a really neat animation showing the effect of wind speed on our drifter trajectories, that the drifters in the coastal areas, their motion is primarily determined by the winds. So it's important to do forecast of ocean currents to have really good forecast of the wind speed. I hate to say, given this particular political climate, a lot of the buoys out in the northern Gulf of Mexico, along the east and west coast of the United States, are not being maintained, are not being replaced. New ones are not going in. So the wind velocities near the coast, the data sets are actually getting poorer when they should be getting better because we have much better technology. Talk to you, Congressman. Anyway, here's a spaghetti plot. We call it spaghetti plot, where we just put all the trajectories together on one plot. And so the one thing that this plot shows you, that there was a significant amount of exchange of water between the coast and the deep water. If you remember the other trajectories that we launched in the deeper water, they made it to the coast. So in this area of the northern Gulf of Mexico, there is significant exchange between the coastal and deeper ocean waters. So it's 5 o'clock. Let me start wrapping this up in saying that real-time currents are needed for accurate prediction of oil movements. Measuring ocean currents is expensive. Those drifters are on the order of $400 or $500 a piece with the contract that was required to track them. And we were tracking them at very high resolution and every 5 to 15 minutes in time. Current meters are expensive. Ship time is expensive, $20,000 to $30,000 a day. One of the things we know from the last 30, 40 years of ocean exploration, and we keep seeing it and learning that it's even more important than we first realized, is the fact that these energetic ocean eddies are very important for transporting dispersant oils. This experiment, the GLAD experiment, the Grand Lagrangian deployment, where we deployed over 300 drifters in the northern Gulf of Mexico, one of the things we realized from that is that the small-scale, sub-mesoscale motion is also extremely important. And we really need to come up with good ideas about how we're going to be able to measure that component of the velocity field, because it is important for dispersant oil. We know that small errors in observations lead to large errors in predicting where the oil goes, and because of these errors in nonlinear dynamic constrains accurate prediction limits to be about 2 to 7 days. In some of the coastal areas close to the coast, the prediction limit is probably about 2 days. In strong circulation features like the loop current errors, eddies, the prediction limit is about 2 to 7 days. So I'm going to stop here. I'll answer your questions, and I'd like to thank you for your time.
Okay, well, thank you very much, Arthur. Like I said, everybody who's on, this is your chance to use our chat box to type in any questions that you have that you'd like to have answered. We'll give everybody a minute or two to think about their questions and get them typed in. Somebody said, as an educator, they're hoping to share some of this with their students. Is there any way they can access some of these animations or drifter movement to show students? I will say we are recording this, so the recording will be up on our website, but do you have any other ideas, Arthur?
On the carth.org website, you can look up most of these animations. We do have the videos online.
Okay, so I'll add that as a resource to your webinar page.
Okay, good. And also, I have an educational website I'm building on surface currents. Just the simplest way to find it is just type ocean surface currents into Google and go to the Miami site, and you can learn a lot more about the loop current and the Florida current on the ocean current website. And we also, you know, since there are some nice companies out there that'll allow you to put stuff online, we have something on Vimeo, vimeo.com/carth. You could also find some of our videos. Thank you, Laura.
Okay, well, I will make sure to go find those as well and put them up on our website along with this presentation. Someone's asking, is there a site that their students can go to learn how to build drifters?
Oh, that's a good question. Do we have anything about building drifters?
Yeah.
Yes.
They should just contact me. We're working on a lesson plan, but it's not quite finished yet.
Probably the best thing to do is to get in touch with Laura Bracken. You could give people her email. We're working on a lesson plan for that. We've previously had some schools engaged, like Mass Academy, in building drifters. And some of the drifters we've launched in our experiments were put together by high school students.
Okay. Let's see. Someone's asked, if the equations behind the numerical models can't be solved by humans, how are computers programmed to do so?
Well, they can't be solved analytically by any analytic method. There's no way you could come up with a theory to fully solve these equations. But there is a way to write the equations in a numerical form where the equations are solved iteratively. So it solves one part, then sends that to another part, which sends it to another part, which sends it back, and there's a lot of information. It requires a tremendous amount of calculations. So yes, we could conceivably do those calculations by hand and come up with an answer, but it's not practical or feasible. The other thing is people make mistakes. Once you have the computer program, it's not going to make any mistakes. Richardson, who British scientist, actually tried to do weather forecasting around the time of World War II in England using a room full of people. And one of the things they found is that, the little mistakes people made in their computations because the nonlinearities caused major problems in the solution. I hope that answers your question. If not, re-ask it, please.
Someone's asking, can these models be used for anything other than oil transport?
Oh, yes. We're using them to predict the state of the ocean. So the atmospheric models, they tell you what the wind, air temperatures are, and whether it's going to rain or not. Ocean models tell you the water velocity, the temperature of the water, and the amount of salts in the water. It tells us the density distribution, the pressure distributions. They're used by the U.S. Navy for military reasons. They're used by scientists in experiments to have an idea of the flow conditions. So there are a lot of uses for these models besides predicting where oil goes. The U.S. Coast Guard uses models to predict. They're not as elaborate as these full-blown models, but they use parameterized, simpler models, but they run it a lot with good data to predict where people are going in search and rescue operations.
The Stony Brook School in Long Island, New York asked if there were any other websites or resources to help their students build some drifters. So you noted that there's a lesson plan possibly coming out through CARS, but do you know of any other sites or resources they could use?
I'll be honest.
I know NOAA does. I can send the website.
NOAA has a website, and Laura will send you a link to that.
Perfect. And just so everyone knows, this Laura that we're talking about used to be a RC regional coordinator for NOSB, so she knows the students really well. She'll make sure you get some good information.
Yeah, we're lucky enough to have her working for Outreach for CARS now.
Yeah. Let's see. Anyone have any other questions? Feel free to type them in. Well, I'll ask the question. Our last presenter made a comment that when there are oil spills or these issues in the Gulf of Mexico, in a sense it's not good, but it's better than other regions because you can mobilize so quickly. How quickly were you able to start working on these models when the BP oil blowout hit?
Well, there was NOAA immediately started working on this. The people in academia took a few days to get spun up. One reason is we didn't have funding to do that particular work at that time, and most of us are overwhelmed with what we have. But on the side, quite a number of oceanographers. It took us about a week to spin everything up. We had models running already in the Gulf of Mexico, and we just had to come up with a way to put in the initial location of the oil into the models. So we were using NOAA's best estimates, estimates that were coming out of the University of South Florida, estimates that ROFS was producing, and with those estimates, we were digitizing that information, using some software then to take the digitized information and produce a file of initial oil location. So we had to do all of that, and but now you know, we have stuff up and running.
Okay, someone has asked if you're at all involved in the recent penalty determination for BP.
Not that I know of.
Okay. We have a few more minutes if anyone else has questions. Any other questions for our presenter? I guess I'll ask you one more question. Since a lot of these coaches are dealing with students who are looking into careers, did you start your career knowing you were going to be an oceanographer, or how did you get to where you are now?
Oh, that's a great question. Well, when I was growing up, I really liked the ocean. I really liked fishing. I happened to be good at math. I realized that early on. So when I was in high school, I went into the guidance counselor. They gave me a big book. We didn't do anything online then. And in this big book, it was about careers. And I, looked up what careers if you're into the ocean and mathematics, and it came out to be physical oceanography. So pretty much in high school, I knew I was going to become a physical oceanographer. I went to Stockton College. I studied both marine science and math. And then I went to the University of Rhode Island. I was very lucky there to be a student of Tom Rossby, who is one of the pioneers in using Lagrangian instruments to measure ocean currents. And at that point, working with a tremendous mentor like Tom Rossby really piqued my interest and kept my interest in physical oceanography. And then after that, I decided, I spent a lot of time looking at data. I needed to do something different, so I went up to Harvard University to work with Alan Robinson and to do numerical model and how to look at the problem of how to put ocean data into ocean models, because that was a number of decades ago, and ocean prediction was a fairly new field back then. So I was at Harvard for a while, and then I came to the University of Miami. The weather's better here. The fishing is much better here. And I ended up working with the remote sensing group, working with sea surface temperature images. So, yeah, I've been into the ocean and looking at how to model and predict the ocean for a long time.
Great, thanks. Okay, well, it doesn't look like we have any other questions coming in. Just a few comments to say thank you, as they really enjoyed the presentation.
You're welcome.
So,
and again, thank you to all your teachers. You have a tough job. I've been in a few schools in outreach, and I really appreciate what you do. I have a hard enough time giving 3 lectures in a row. You're all giving much more than that every day, so thank you.
Well, so everyone knows, we will have the recording of this webinar posted up on our website. Just go to www.nosb.org. It will be up tomorrow morning, and we will try to get as many of these other resources that they've been talking about, CARS, Ocean Surface Currents at Miami, the Vimeo, and some of these lesson plans from CARS. We'll try to get those up on the website as soon as possible as well. We will also be posting these webinars on our YouTube site shortly, so you can just search YouTube if you need to find them. And as I said earlier, please share these recordings with other educators and obviously with your students and NOSB teams. Our next webinar will be Tuesday, January 27th. Dr. Joseph Montoya from Georgia Institute of Technology is going to be speaking about the ecosystem impacts of oil. So we've done chemistry, physical oceanography, now we're getting sort of into the biology and ecosystem impacts. And we will be advertising this webinar just like we have been for the past 3 or 2. So look for an email from us later this week with all the information that you need. Again, please share that with anyone who might be interested. And thank you for attending the webinar. We're really glad you could join us today. And Arthur, thank you very much for presenting. I think everyone really enjoyed this, and this is something that's very different from what we've had presentations done in the past. So thank you.
You're welcome. It was fun.
Okay. Thank you, everyone. Have a good evening.